Hello again, friends. So it has been a minute, and there's been some changes. I hope you will notice that my audio is a lot better. I finally decided to get an actual headset. Definitely feels weird as I can't hear myself as well, but you guys can definitely hear me a lot better. And I should know what the heck I'm saying or what information might be coming out of my mouth at this moment. Um, also, I had to take a bit of a break. Suffered a bit of a head injury. So apologies for how long it's been since I've been able to put out a video. But I was actually kind of happy. I saw that I didn't do any sort of promotion for my last video, and it actually has done the best out of all of the videos I have. And so I don't think I'll ever actually be able to um, make this a full time thing where I can focus on the channel. Unfortunately, just because Haskell is so unknown and still very much a niche thing, but I hope that will change, and not for the sake of monetization, but for the same reason that I'm doing this channel to begin with, which is also not for monetization. But just because Haskell is such a beautiful language, and there's not really, again, not really an easy sort of simple way to attack learning the language that you can just sort of get started with. Um, but that said, I hope, um, I hope me getting a headphone kind of shows I am truly interested in a lot of feedback for the channel, especially in terms of what topics you guys would like to see. Maybe you started learning through simple Haskell or really whatever, and there's another topic that this is quite challenging. I'd love to hear what sort of topics you find are extremely challenging in Haskell, and you think would be like a great video about. And I'm sure that you know with how with how well organized the Haskell language is, that you know your suggestion would be the same as many other people. I have my email on my channel, but I'll just put it here just in case you ever want to give some feedback on what would be a great video option. I will be doing. I know this is a long introduction. Apologies for that, but I will be doing a lot more, as I said before, a lot more libraries. In particular, I'm going to do sort of a spotlight on Reflex and Obelisk, which are really the actual reason I decided to learn Haskell, because the tools are just extremely powerful. Um, but yeah, there's not really much good resources that I've been able to dig up in terms of quickly learning such things. There is definitely documentation they have, for the library and for the Obelisk framework, but it's kind of hidden and kind of random. It's just very easy to miss, and it never, in my opinion, the explanations are very much focused on being as mathematically rigorous as possible, which is great, is definitely a useful thing, but I think is not as valuable as just a simple explanation that your brain can kind of start to chew on and start to get going with, and then build on as you learn and start to realize your false assumptions. Anyways, so kind of realized that I have talked about laziness and strictness in other videos, but I've never actually done a video on the topic itself. Um, and so it's actually quite simple. I don't. This is not going to be a long video at all. And yeah, uh, so the way I've talked about it in other videos has definitely been regarding lists and that sort of thing. But the number one preface that I should make here is everything in Haskell is by default lazy. And so what does this mean? Well, if we have 1 plus 1 plus 1 plus 1, we can all, I think we're all at a level of intelligence to understand that this equals 4. And so obviously the compiler can too. and the compiler could evaluate this so that we end up with 4. But of course, that takes a little bit of work. We actually have to, run the function of plus with our 2 arguments, right? This will give us 2, and then that will feed into, um, you know, uh, well, if I was to use it, okay, never mind. I won't say that. But we could continue to add 1 plus 1, right? So we get to 2, kind of like a folder, right? Where we're just adding up the values, and we would get to our value of 4. Right. My point being that there is actual work, actual evaluation that needs to happen in order for us to get that result. And so this is tiny. It's trivial here. And we definitely don't need a computer program to tell us what the answer is here. But we didn't build or they didn't build a language for this sort of problem. Um, and so before I move on to a better example, I just want to say that this is called, so the unevaluated, in terms of the language around this unevaluated kind of code chunk here, it's called a thunk. And so Haskell will keep thunks until the result of them is demanded. So what does this mean? So if I had a program, and this is actually impossible because we had to have a main function. But if I had a program that we said x is equal to 1 plus 1 plus 1 plus 1 plus 1, I've lost track. But this would not do anything. This is just an expression that could evaluate, and so I'm forgetting the language actually. I'll I believe I forget which one is which. It doesn't really matter. Again, I'm not really a person super strict on my language, and I don't think it matters because what matters is the actual concept. That's my excuse. Um, but I believe this is called. Yes, this makes sense actually. Weak head normal form, in that it is unevaluated, and so if once we evaluate it to 4, it would be in normal form, or normalized. Um, but that doesn't really affect how we compute. So when would we actually demand this? Well, we don't demand, like, right, if this is Python, we demand the value of x as soon as we initialize it. Whereas in Haskell, we would only initialize it when we do, or sorry, we only evaluate the value of x when we say print x. So print x is going to force the evaluation of x because the print function is going to create a side effect which actually demands that result. And so that actually kind of brings up another good point. What if this was, let's say, my function is func, and I have another function, uh, you know, 1 plus x. Is this going to evaluate? And the answer is it depends. It depends on if func has been demanded. So now if we go back to main and we say print func, which is not really a func, it's more an expression. Let's call it an expression. Then yes, x will be demanded and so will expression. Expression will be demanded first, and by demanding expression, we demand that the thunk of x is evaluated, which ends up with us having an evaluated expression here being equal to 5. And so we are going to print this. It's going to show up in our terminal, and that's what's going to cause it to evaluate. And I think I mentioned this in the I/O video, but it actually used to not be a thing at all. When the Haskell language started, it was a research language, and according to Simon Payton and Jones, you could not do side effects. Which is kind of interesting, but that's really a different thing. But I will say why I bring that up is that side effects are what's actually demanding the evaluation of this value. Right? So, other languages we could. Um, this might be easier to think about in other languages, but we could, in theory, build something that adds to infinity and never show evidence of that building to infinity, right? We just have some Python while loop that, or really any while loop in any language. I just have most familiar with Python. It's top of mind, but we could have some Python while loop which adds to a value until it reaches infinity, and then never show the value of that value, or never show, sorry, yeah, the value of that variable. Um, and we would create a lot of heat on our computer. However, in the case of Haskell, if we had a function, for example, or sorry, a variable, and we're gonna have a variable. This is where kind of I think Haskell laziness starts to become really cool. Um, is we have a variable x, and it is an infinite list, and that just worked. It is done instantiating the variable x, or the expression, or namespace, whatever you want to call it. X equals is now instantiated, and it's an infinite list. And so I can say, for example, take 9 from x, take 10 from x, and that was quite quick for an infinite list. Very, very quick for an infinite list. So, like, what happened here? Did we create the entire list and then take 9? No. Take is a great function for demonstrating this laziness with lists, and as we'll see, lists kind of, um, you know, are basically how everything works in a way. In the laziness sense, I will say, but I will explain that further. But now, we're only so take 9x. What this is saying, and so take, we can look at the value, or the type of take, and I think it actually might be kind of interesting. It might actually even tie into. Just gonna thinking out loud there. It might even tie into the next part. No, it won't. Never mind. Okay. Well, this is what take is, and what is this saying? 0 is less than n. Take. Oh, because it's recursively decrementing that. So it's just going to continue going through the list and peeling off unsaved take, I believe. Just what does this do? This just peels it off and adds it to our output list, right? So it peels off from the starting list and is going to return it into our end list. Uh, and it's doing so by building the new list. As you can see here, x from the old list, place it, and then cons it to the result, the result of the recursion, us taking from the other list. And so the point here is, we could continue to dive down deeper and deeper and deeper and deeper, asking, like, where is this laziness coming from? And well, it's built into the language. Now, true, like, but where is that laziness coming from? How does that laziness, like, actually sort of work? And I guess the best way to answer that question is to look at the data type of lists, which is either constructed as an empty list or a cons list of A, I believe it was. So, or if you prefer, we could write it kind of like this to get the sense of it. But I'm just going to say, let's keep it familiar and represent it like this. Um, and so where the actual laziness in this comes from is that um, it's very easy to this is a recursively defined type, and we can just continue to peel off the next element of the list with a representation of some rest of the list. And so, in this sense, peeling away from the list itself is sorry, I just got a text, but distractions. Let me throw my phone away. Pardon me. Um, Peeling away from the infinite list just leaves us with some infinite list, and so we're not actually, and so what that means really is in taking this part, we don't have to like there's no actual reason for the compiler. I guess the rest of the answer is it's how the compiler works, um, which you could learn more about, but I don't think is worth getting into here. Nor would I be the best subject matter expert for that. Imagine there's better wikis out there, and so we only need to pull off the start of the list in order to keep it as um, a valid case of a data type. And so even with the and in doing so, there's nothing that forces us in that action to evaluate the rest of the list. And so while this is true in any language, the Haskell compiler is the only language that actually sort of implements that. Um, yeah, and so again, easiest to see through take. I would really suggest just diving into take to understand how laziness itself works, um, and it's important to note too that um, or now let's think about this in a nicer fashion. Um, I have a function which does web scraping, and when it sees a web form, it can uh, enumerate all possibilities that web form could create, and like all possibilities with respect to its options that it gives. So if it has a drop down list, a radio button, or sorry, radio input, it can enumerate all the different possibilities between the different inputs. And so this list is absolutely massive. Absolutely massive. And I can't possibly evaluate that and then keep on going. But what I can do is I can do something like, um, well, I can apply a function throughout that list. And and again, this just really builds on the idea of take. Take, of course, you could definitely write take in terms of uncons, which I mean they're kind of doing. Sorry, what am I saying? They are doing, just doing it through syntax, and uncons just literally being like take this. Um, but because of laziness, I can now peel off one list element at a time and apply a function to it, right? And so if this is an infinite list, all I need to do, right, the actual step that the Haskell compiler or the order of operations that the Haskell compiler is going to take is it's going to say, if we think about it in terms of fmap, so we're going to fmap f onto this infinite list. It is, we could even do some sort of like fmap. I don't know if this actually exists because I don't see the point of this, but sort of fmap take, where we take from an infinite list and map some f over it. What's going to happen here is that we're going to apply f to 1. We're going to evaluate, and I'm assuming that we're doing some output. We are, let's say, we're enumerating these. Actually, here's what we're doing. We're enumerating these form URL possibilities, and then performing a web request on them. And so, if I have, uh, let's say that these represent just options, and we got 1 and true. And then we have another one, which is 2 and true. Another one, let's see. We're going to assume there's only 2 there, so 1 and false. This would be, I suppose, an enumeration for really just 2 options, which have two binary options in the sense that each option have 4. So this is no longer an infinite list, but we're just going to pretend it is because this is again a simplified example. So you know, use some imagination, I suppose, which is not the proper thing to say as a teacher. But let me think here. Yes. Oh, 2 and false. So, anyways, we're just going to assume for some reason that is an infinite list in terms of understanding the actual laziness part of it. So what I'm going to do is I'm going to apply f to 1, and f to 1 is going to give me, we're going to say that f is, it takes a URL and, a tuple of int and bool, and gives me a URL. And I'm going to have a second function, make request. It's going to take a URL and do do a web request, do some IO side effects. And so if I say make request f1, and I'm, this is now where fmap no longer makes sense, because in this sense, if I was to fmap, and you still have to think about the order of operations in which you are saying to the compiler, if I was to say this right now that I want to, if we call this list, we're going to call this list my list. And we're just going to, again, just pretend it's infinite. I don't know if I can say that there though. I don't believe it would do that. I don't know. I actually have seen some tricks you can do with the syntax there, but I don't know of them, nor care for them right at the moment. But yeah, we're just again pretending it's an infinite list. So if we said that we're going to fmap f to my list, and then we're going to make request. I guess we're also going to, map m, which I will explain in a second, and I might actually have already explained in a previous video. I think I did through traversable. So I recommend looking at traversable. Yes, traversable to understand a little bit better about map m. But if I say, map m make request, fmap f list, f my list, then this is going to force the evaluation of the entire list. And so if we are still pretending that we have an infinite list here, then this is going to cause a problem. And we're going to have to fmap the entire list before we can even make a single or perform make request a singular time. However, we don't really need fmap in this sense. I could say something like map m make request f. I believe this would work for syntax if we said that should work. Yeah, that should work because URL would fit into that way. So we go into bool URL, boom boom, to IO. And so that's why we can chain it, and we're just going to map m make request dot f to my list. Now this is going to work and take on the full power of laziness, and this is actually a problem I ran into with using laziness. I was like why is my function taking so long? And then I realized I had to refactor it a little bit so that I didn't force strict evaluation. Or, sorry, so not strict evaluation. That's kind of the wrong way to say it. Not that I didn't force evaluation. Uh, but yeah. And so, again, if you do this way, just to drive it home, it will make the turn it into a URL and then make the request one at a time. And so, we could stop our program before it's completed, and it will have processed some some number of elements in that infinite or massive list, right? And so, in the actual case of my URL enumerator, it's not an infinite list, but it is like literally the one example I saw, which had 89 inputs, was pretty big. I don't know what 89 factorial is, but yeah. Um, so yeah, I don't even know if it'd be 89 factorial. Come to think of it, I don't know. I'm not a mathematician. Um, anyways, so that's the core of what laziness is and how to take advantage of it. What is strict though? Um, Actually, I should continue. Well, and this kind of extends. I should just lastly say before moving on that this kind of extends to a function we'll see fix, which is really it's cool to look at. Um, like so, this is how it's defined. Fix f equals let x equals fx in x. Like it's which is like what? Oh, what exactly is this? What is this doing here? This is interesting. Um, let's do this. Let's give it a function. So we have to give it a function. According to the type signature, we have to give it a function which takes an a and returns an a. So let's take x and add 1 to it. Um, yeah. And this is gonna blow up, I believe. What happens here? Oh, I need imports. Data.function. This isn't how you use it. I forget how to actually use it. Here, let me try and find an example quick. All right, Stack Overflow for the win. Um, so it's basically here's how you actually use it. And it doesn't make a whole lot of sense to use it without. So what Fix is always building an infinite list, where you're generating the infinite list in sort of a neat way. Um, so I could say, what can I say? Let me see if I can do sum of x. Oop. Except that's gonna be, yeah. Oh wait, what am I saying? That's sum of x. It's an easier one I could have done. Let's do. I don't know. No, wait, it's a list. I guess you know what? I don't care. I lost interest. I don't. You never actually use fix, but it's just an interesting example of laziness. Mfix does come into use a lot more with as we'll see in an upcoming series I'm doing, Spotlight on Reflex. So, but we will get to that. So yeah. Anyways, though, how do we force strictness? And there's two main ways. I brought into context or into just I don't know into speak um, this function here because I think it's kind of I think it's the easiest way to think about um, easiest way to explain strictness. So the thing that might trip you up, because yeah, it kind of tripped me up just mentally a bit, is like how to actually like apply strictness, how to you know like where do you notate that you have to have strictness here, and so for example, um, if we wanted to do, actually that's kind of weird because it's a let's do this. I think this should work. Yes. So yeah, this is maybe a good example. I had to use since this is an infix operator, I just made this a non-infix operator, a which is a default infix operator. You can just put it in brackets. You might have seen the other videos, or just know that by now. But in case you don't know, so what this is saying is that um, I'm going to add um, 1 and 1 plus 1 plus 1, and I am forcing the right side to be strict. So, or strictly evaluated at the time that this function is called. So by the time this function is, instantiated or the actual expression is read, we might have something like 1 and 3. But that doesn't mean that the actual plus itself is strict. Just the input to plus, not plus itself, right? And just to repeat that because this is where I mentally kind of got lost, or kind of confused. Is it's in the inputs, which makes sense, um, in terms of how to apply strictness, and um, yeah, because I mean, even like the end output of your program really is going to be strictly evaluated. So or evaluated, I should say. Whatever the last kind of thing is, that you return is going to be evaluated, and whatever thunks need to be evaluated in order to build up to that final result will be, therefore evaluated. But this is just saying I don't care whether or not this thing was actually demanded or might be demanded. Do force the execution of this. And so why would you want to say that if you're not actually going to use if you might not use the actual value there? And I think a good example could be uh, hmm, what could be a good example here? Well, so with scraping, I always end up having these massive lists, and there's definitely ways in which I could sort of start to summarize those lists and um, and so actually an example I had was I accumulate. I have a monoid and state. I have my state being a list of. Actually, no, sorry. Let's for the example, I'll just say that um, the state is an int, and the inner thing was IO, and this is state t. And I'm keeping int as state, but where this int is coming from is that I have a stream of input naturally from my program, right? Just naturally in terms of like the problem, there is a stream that sort of starts to show itself, and that I have multiple pages, which is really therefore going to result in the stream because I have to do some evaluation of those pages across the broad spectrum of my pages. Putting those results together, right? Combining those results together, which is really now kind of defining the essence of what a monoid is. Um, and so, don't at me if you're like a specialist in Haskell watching these videos. Appreciate the feedback. If you have any disagreements with that analysis of what a monoid is, but that's effectively what it is. Now, Um, so what's actually going to happen to go from this stream to this int is that I'm going to say, I'm going to continually, each iteration in my monad, I'm going to get state, which I believe I could do just by getting this, and this is going to give me state. Yes, that's correct. This is in a monad. Let's just call this monadic func, and this is a state, and I do some action, which gets me, some action results in another input to track, and I am just going to put state with a state, or put state plus new input. Or maybe this new input is itself a list, and so I'm just going to take the length of input, or of the new input, and then I'm going to put that entire thing to state. But again, all of Haskell is lazy. You might be, inclined to think just from looking at other languages and reading other languages that this is going to evaluate and then put to state. That would be a fair default assumption. However, it's not. It's going to put the thunk to state. So if I have already in state, 1 plus 2 plus 3 plus 4, then state is going to really, under the hood, be equal to 1 plus 2 plus 3 plus 4, unless I've forced it to evaluate for some reason. I might have grabbed state and said, depending on the type of, depending on the value of state, do some action. I might have pattern matched on state, in which case I would force state to evaluate, and then it would be like this. But it also could actually, under the hood, be an unevaluated thunk, if that has not happened. And so, assuming it's an unevaluated thunk, then what this is going to be is now plus the length of new input. And really even, like if length of new input is what we're adding here, this is probably really like length of new input from last iteration. And I'm just going to put in all caps because this is not a real variable. And yeah. Right? It's from the last iteration, and it has still not been evaluated, but again, just for the sake of our evaluation, our mental evaluation of things, we are going to assume it's just like that. And I'm getting a call right now. 1 second. This is from my mom. Sorry about that. Parents came by with a housewarming gift. And so, almost just about done here. All there is really left to say, besides an honorable mention, is just that the other way is to use, other way to enforce strictness on variables is by the use of the language extension bang patterns. And so this would be at the top of our module. I'm just going to do it here quickly, and then I'll copy it to the top. Just because it feels like an easier way to think. I don't know. Oh my gosh. Bang patterns. And that will allow me to say that f, which takes the arguments x and y, does whatever with them. So we might just do x, I guess an equivalent way to what we're doing here is really just x plus y, and this is going to force both 1 and 1 plus 1 plus 1 to be strictly evaluated. And note too that like this kind of goes back into there's definitely a point to be made here about type signatures, because if we look at the type signature of 1, we're going to find an obvious answer here. That's a num. We could also think of it as just an integer or int. 1 plus is, that's going to cause an issue because it wants to be infix, so it does not know how to parse that. This is saying that is, you know, an A to A, and that it takes an argument. And then if we do this, we find that when we apply it, we find that it is now reduced to what is effectively just a num. Right? Once we apply a function, it's reduced to being, at the end of the day, a value. Right? Every function, once it's applied, I was gonna say once it's applied, but oof, fancy. Once it's applied, becomes a value, except a lazy value, often, or by default. Um, but yeah, and so um, now I suppose we could do something to force the well, no, no, we couldn't. But yeah, that's effectively how we eliminate laziness. In strictness, once we understand laziness is actually quite simple. I don't think there's really much to say to add to what we've already talked about. Um, but yeah. So, and I will say there's also a concept of lazy I/O, except um, it would definitely warrant its own video if we were to go into it. It's not. Um, I don't. I've never used it. There's not always a good case for it. Like, the one time that I was going to look into it and learn about it and then implement it, I found that there was actually a better solution than to even use lazy I/O, and the reason for that is because it has, or I believe it's explained that it's the same as using unsafe interleave IO. Just gonna write that out. Unsafe interleave IO. And what does it mean to interleave? That you're interleaving actions. So, for example, if we have get line is really get care, multiple times, right? I think it's how can we do this? If we do um, well, we could simply just say map m get car, and this is a way we could implement um, one to the length of the actual. If we got the length of the file or whatever, but we could. The point I'm trying to get to, it might even just be best to look up literally how getLine is implemented, and that it's basically doing get car but multiple times. And I don't think it's actually literally using get car, just because there might be some things that are you don't want to repeat every single time. I don't know. I didn't implement it. But the point here is that um, we would only force get line to evaluate getting one character at a time. And so, since that's being interleaved with other actions, we might also be writing to the file at the same time, and so there's a possibility for a lot of errors. And so that I just wanted to give a mention to lazy I/O, but that's really the gist of it. In that, because it's lazy, you do allow for some uh, unintended consequences. But if you are interested in it, I definitely recommend checking it out. And there is ways to, just be conscious of like everything in IO and Haskell. It's really just it's called unsafe because not because it's going to blow up your computer. This is not that new VR headset that is going to kill you if you die in the game. I don't I don't imagine the Haskell compiler will ever implement that for users of the language. That just doesn't seem very productive. Um, you know, and so yeah, recommend. But anyways, I'm definitely rambling at this point. And that is really the contents of our video. Thank you so much for watching. Again, any comments, questions, feedback, all of that, please do let me know. And happy Remembrance Day. Oh wait, no, it's oh my gosh, that's just my clock being off. I am an idiot. Um, but in advance, happy remember, a good Remembrance Day. But anyways, thank you so much for watching, and hope you have a good night and happy coding.